All right, good morning, everyone. So, welcome to our last class of the quarter. So today is kind of a fun class. We're just going to focus on Faraday's law and look at some examples and do some demonstrations. Really, that one equation that I boxed last day is the equation that we'll focus on. And so next week, I'll have office hours Tuesday, Wednesday, Thursday from 1 to 3 p.m. in my office. I'll also host them via Zoom, so you can basically look at what's going on in the office if you don't want to come to the office, but you still want to see other questions that people are asking, or even ask a question over Zoom. So I'll send all that information via email. Yes?
For the homework, can we turn it in office hours or just?
Office hours, you can turn in the homework to my mailbox. That's where you should turn it in. 180-204. You'll turn in the homework. All right, so let's get started. Now, what I have here is, we've been talking a little bit about magnetic field. Now here's a magnetic field due to a solenoid. And this solenoid, you can actually see the rings that are different. It's really just the field due to a bunch of rings that are added together. But what we found when we looked at Faraday's law is something interesting happens when you create a field or destroy a field. So look what happens when the field turns on. That's where the EMF itself is induced, is when the magnetic field is changing. Okay, so writing it up on the board again, what we have is Faraday's law. Which says an EMF is induced when the magnetic flux is changing. And the negative sign again tells us that the induced field always tries to oppose the change in the field. Okay, so let's look at an example here. All right, so if you want to take out your voting cards. So last day we looked at when you move a conductor through a magnetic field, we saw that the charge separates. And when the charge separates, you get an induced EMF. Now if you connect that conductor to a closed loop, you can get a current which is flowing. So let's try to test this out here with the following example. So let's say there's a rod, a conducting rod, which is rolling along a conducting rail to the right, with a magnetic field to the right, and as that rod's being pulled along to the right, is there an induced current? If so, what is the direction of the induced current in this particular circuit? Give you a moment to prepare your vote individually here. All right, let's take a vote on the count of 3, 2, 1. Some of you are still thinking about this, and I see some C's and some A's. All right, just take 30 seconds. Just convince your neighbor as to the explanation. The explanation is what's important here.
Because the area, the magnetic field is going in the same way, so they're not. There's no crosswalk. Like magnetic field and the vector, like the velocity vector. Oh yeah. Or the area vector. The area vector. Yeah, they are. Yeah, because
Wouldn't the conductor not be? So when are your
All right, so let's take another vote. And get ready to show your vote on the count of 3, 2, 1. It looks like we have converged. Some people are missing cards back here. C. Yeah, there is no induced current. The reason there's no induced current is because there's no flux through this loop right here. So, right, there's no magnetic field flowing through the loop. So there's no changing flux. There's no changing flux. There's no EMF. If there's no EMF, EMF is what drives the current. It's that electromotive force. Right? EMF is just an electric field. Yes, Will?
Could you also just say that since the field is just uniform, like there is no change in flux as well? Like regardless of like the transition, like since it's uniform, like it wouldn't change at all?
Excellent question. And would that in fact be true? So let's imagine like the picture that I drew on the board last day where the field was, I believe, going into the board. It was a uniform field, but as I pulled the rod to the right, the total amount of flux was getting bigger, not because the field was changing strength, but because the area was getting larger. So in that case, the flux was increasing, not due to the fact that the field was changing, but the size of the loop was changing. So there's different ways. This is an excellent question because there's different ways you can change flux. You can change flux by increasing the field strength, increasing the area, or changing the orientation between the field and the area. Excellent question. All right, so let's look at another example here. So a conducting loop right here is halfway into a magnetic field. Suppose the magnetic field begins to increase rapidly. So these crosses represent, or these X's, I should say, represent magnetic field, which is into the board. And this loop is just sitting there, and the field is increasing rapidly in strength. The question is, what happens to the loop? I've given you 1, 2, 3, 4, 5 different options. So take a moment to quietly think about which of these options best describes what's going to happen to this loop as the field increases in strength into the board. All right, I'll give you another moment to prepare your vote. And let's get ready to show our votes on 3, 2, 1. All right, a little bit of disagreement. I want you to explain to your neighbor as concisely as you can which option makes the most sense.
And B increases in.
I said I said it would be purple because of the right hand rule.
And that's
Because and I think the way it is, like, EMF goes towards us,
induced current
so that
right? Create a magnetic field that counteracts the current will be going clockwise, right?
Clockwise. So the magnetic field of the induced current is going up.
Yeah, the magnetic field is going in. Yeah, the force should be going left, right?
It's saying it's going up. In reference to the page.
Oh, in reference to the page going up.
If it's being pushed, it would just go to the right.
yeah.
Oh, yeah, okay, yeah, no, indeed. It's pushed out of the magnetic field.
Yeah, it would be
Out of the page towards us.
Yeah, and so if you push like this.
All right, a couple more seconds here. You're going to get ready to prepare your vote. All right, so let's get ready to prepare your vote here. And on 3, 2, 1. All right, I'm looking around. There's a lot of D's. Seems to be about 60% D's and about 30% B's. So D is right. The loop gets pushed to the right. Now the reason the loop gets pushed to the right is because as the field strength increases into the board, there's an induced current in the loop, which wants to basically oppose that increasing field. So the loop wants to create a field that's out of the board to basically bring it back to what it was originally. Now, how are you going to create a field out of the board in this region of the space right here? Well, the only way to do that is by creating a counterclockwise current. That creates a field that is out of the board inside the loop. So we have a current that's induced in the counterclockwise direction. If there's a counterclockwise current, if I just think about, well, current in a magnetic field, it's going to experience a force. The bottom wire, current is this way, magnetic field in, force up. There's no force on either of these chunks of the wire because they're not in a field. But this chunk of the wire here has current, field, force down. So those two forces cancel. But then the wire that's down, current, field, force to the right. So there's a net force to the right on this loop. Now if this loop was entirely inside the magnetic field, there'd be no net force, right? Because the force would cancel out. There'd be a pushing back on this case. So the loop is pushed to the right. Now also too, the tension does increase in the loop as well because the top and bottom are being pushed together. So if it was strong enough, it could, say it was a really strong field, say the field created by a superconducting electromagnet, it could say crush the loop because the force would be so strong. All right, so any questions on this one here? Makes sense? Okay, let's try another example where this time I'm not, the previous example what I was doing is I was changing the magnetic field. This time I'm not changing the magnetic field, but what I'm doing is I'm dragging a loop into a region of uniform field which now points out of the board. Okay, and this F force, this is just so snapshots of the ring at different locations, and I'm pulling the loop to the right with a force. And that force is going to change depending on where the loop is located. So the question I have for you is, which pulling force is largest that must be applied to keep the loop moving at constant speed? So where am I pulling the loop the hardest if I want to keep it moving at the speed it starts out with here? So it always has the same speed. Let's take a moment and think about this quietly. All right, let's take our initial vote here. Which force is the largest? Okay. All right, I want to take a moment to discuss this. So explain, using what we know about magnetic fields and changing magnetic fields to your neighbor, which option you think is correct. Option or options, say. There could be more than one force, which is the largest.
Okay, so I said that B is the largest.
Yeah.
I wasn't sure about this, so why?
Because for C, the forces are canceled out because it's counterclockwise wheel. So that means basically the forces just get canceled out. With B, with the right hand rule, it goes like this, right? So that means and for D, the force would be going the opposite direction. Oh, wait a minute. Actually, wait a minute. When it says which force is the largest, does direction matter?
Yes. No, sorry.
Yeah, I would say the largest net because they both increase. Or no, we're just saying which of those forces has to be the largest pulling force? Because the force is going downward, right? The force is going downward.
Or no, yeah, the magnetic field is down. Or no, I think it's up.
So magnetic field is kind of opposite.
All right, let's take a vote here.
And the force from the magnetic conductor is down.
Okay, let's show our color on 3, 2, 1. So I'm seeing B or B and D. Most are saying B, but there's some B and D. So, all right, well, let's talk about this. Which one would be correct? Well, B, I think, would be the largest. Let's discuss this here and see that it is in fact true. It doesn't take any force to pull it right here. Let's say we're not considering, say, air resistance. You're just pulling it along. There's no drag, right? You just pull it along smoothly. But as as this loop enters into the magnetic field, what actually happens is this magnetic field is pointing out of the board. It doesn't like an increasing flux through it, so it wants to create a flux into the board, or magnetic field into the board to oppose the flux that is increasing out. So how do you create a flux into the board? Well, you need a current that goes, this time in the clockwise direction, to give you a field on the inside into the board. So if I have a current going around in the clockwise direction on this segment of the wire right here, current is down, field is out, force is back. So there's a large force backwards. So to get this wire into the magnetic field, you have to pull it in. Because the flux is rapidly increasing, there's no force here, but when it exits the loop over here, it actually gets kicked out of the field. So in a sense, the field actually pushes the loop out. So to get it into the field, you have to tug it in. For it to leave the field, it actually gets pushed out. So the force would be backwards. Yes?
When it's leaving the field, will it induce a current that will create a magnetic field also coming out of the board since it wants to resist the change in flux?
Exactly. Now the flux is decreasing. It wants to restore that flux. So it creates a current now in the counterclockwise direction. And that counterclockwise direction, well actually, let's see. Create in a counterclockwise direction in that direction, right? So current is down. On this section of the wire, the current is down. The field is out. So the force is this way.
Won't it be trying to keep it in at D?
You're correct, yeah. So I misspoke there. Yeah, so it seems like now that we're discussing, it seems like B and D are both equal in magnitude because it's being resisted pulling in and it's being resisted pulling out. Both cases. So if you said B and D, then you're correct. Those are the largest forces. You have to pull. A and C, in fact, would be 0. Thank you. Yeah, good question. Yes, Elijah.
Don't you figure out the direction of the current when it's being pulled in?
When it's being pulled in,
Yeah.
the flux this way is increasing.
Yes.
You want to decrease it by creating a flux that way.
Yeah.
So inside the loop, you need a field that points in. The only way to get a field inside the loop is to create a current that goes around in this direction to give you a field that's into the board.
Do you get that with the right-hand rule?
Well, in terms of the right-hand rule, that's when you put your thumb in the direction of the current and your fingers curl in the direction of the magnetic field.
Oh, actually, yeah, you use EMF.
Yes.
You do that, yeah. Use the B current.
Okay, so take 30 seconds. Just convince your neighbor that this makes sense, and then we'll move on to the next one.
Okay, so down, magnetic field up.
So current's down this way.
Wait till the magnetic field.
Okay. Oh.
Yeah, it's confusing.
The charge, yeah. So oh, I got it. I was just.
Oh yeah. I did. I clicked on the
What's that?
Yeah, that's true.
Induced field doesn't act on the
Yeah,
induced field is only inside the loop, but not on
I can never get that like I said ice is like cold resistance or whatever.
That means the force is trying to accelerate it, so you need to apply like a resistant force. Yeah. So the only one that's harder. Yeah, because basically FB is equal to negative FD. Yeah. Also, make sure to explain the medicine skills about which ones are unacceptable to use and which one he said he used the constant on some of the just the wires.
Yeah, it kind of is.
Okay, cool.
He was kind of worried about pollution. Coronavirus.
Oh, yeah, that's true. I am as well, yeah.
But what do you remember sending her about? She's like, I'm not fine. I'm not like those old fuckers. I mean, I kind of believe that though.
All right.
It's like in the back, just doing hook shots and just fucking around. Dude's got the spirit.
Any final questions on this one here? Yes, Lydia.
I still don't really understand for D because I think wouldn't the force be pushing outwards as well, like the way they bring it?
So the force, remember, will never be parallel to the field. Because the force is always going to be perpendicular to both the speed and the field. So if you have a field that's outwards, you could never have a force that's outwards as well.
Like not out of the board, but like towards the direction.
Yes, Ryan?
I might be able to help that. So the force is going to be pushing in that way, but the question is asking what the point force is required to keep the loop at a constant speed. So even though it is easier to, like, it's going to be, yeah, accelerate. So you need to put a resisting force to stop it from accelerating.
Yeah, that makes sense.
Thank you very much. Excellent. All right, so what I want to look at now is to try to tie some of the threads of the course together here, because we've looked at some of the different laws of electricity and magnetism here. Now, I want to try to put some of these together here. So, remember this right here, called Gauss's law? Now, Gauss's law, basically, written in this form, is called the integral form or the global form. It basically relates the electric field around over some area to how much charge is inside. Now, equivalently, we can also write out a surface integral for magnetic field. And it turns out that V dot dA equals 0. And this is just to say that there are no magnetic monopoles. So there are electric charges, which are the sources of fields. That's what Gauss's law says. But there's no magnetic charges, which are the source of magnetic fields. Or if I calculate the flux through a closed surface of magnetic field, I always get 0. Right? You can see why physicists would want to have sort of a QM here, a magnetic charge. It would make the equations look similar, but magnetic fields don't have it. It equals 0. Okay? Now, we also then came to, so here's Gauss's law. And then what I've written on the other board, that is Faraday's law, which can also be written as the integral of E dot ds. That's my EMF. And that equals negative d flux dt. So here's Faraday's law. Right, the law that we've been discussing so far. And then there's one more law that we've looked at so far, and that is called Ampere's law. Ampere's law says the line integral of B dot ds around a closed loop equals mu naught I enclosed. Question?
So those first two are surface integrals and the second two are line integrals?
Exactly, yes. So these two are line integrals, and that's Why I call them integral equations is because it looks over some region of space. You're integrating over some region of space to say something about the properties of electric and magnetic field. Okay, so this is how we've written Ampere's law, and pretty much the only way that we'll use it in this course. But it turns out that this law, as we've written it, is not entirely correct. So let me see if I can help motivate why that's not entirely correct. And the reason is, imagine I have a capacitor which is charging. Right, so as I'm charging a capacitor, there's a current coming in, there's a current going out. Now, we already know that in this region of space right here, there should be a B field. U naught I over 2 pi r. There's also a B field here. Right, but there's no current in between the plates of the capacitor, so does that mean that the B field in this third region equals 0? Well, it would be kind of strange if you were moving along out here, you had a finite B field, and all of a sudden it dropped to 0, and then it came back on again as you went through the plates of the capacitor. So it turns out if you actually do the experiment, that is, just bring a compass needle along a wire, what you find is that the compass needle does continue to be deflected in this region as the capacitor is charging. So now we have to account for the fact that the electric field is deflecting, but there's no current. Right? So it turns out there's another source of current which actually creates a magnetic field, and this is called displacement current. Displacement current. So displacement current actually depends on a changing electric flux. And as you charge a capacitor, the electric flux is changing. So in fact, this displacement current actually creates a magnetic field. So the magnetic field is continuous through this region. Now this was kind of a discovery which was by no means obvious, but that allowed physicists to complete Maxwell's equations, which that means Ampere's law really has an additional term, and that's mu naught epsilon naught partial phi sub E with respect to t. Right, now for calculation purposes, we'll never really use this term, but I just wanted to let you know that that term is actually there when we calculate the complete form of Ampere's law. Yes?
Why is it partial derivatives versus just regular?
Well, flux, well, you can think of it as regular derivative.
Okay.
Yeah, complete derivative. Yes?
Well, we need to know how to calculate that.
Well, we already know how to calculate flux, but like I said, we won't be really doing any calculations with
nothing with
displacement current. Right now, so in a sense, everything we've done so far mathematically is expressed in those 4 equations. Okay? And if you go on, if you take another course in electricity and magnetism, you'll probably see those equations again, so I just wanted to write them up on the board. For practical purposes, you know, the ones we only really use are Gauss's law. We're going to use this one in some simple forms, and then we're going to use this one, but not really with that term in it. We'll just have constant electric field. Okay? Right? But then I also want to point out that there's another way to express these equations, and that is I can write them in an equivalent form, what's called a differential form. So this equation I can write as divergence of E equals rho over epsilon naught, the divergence of B equals 0. And Faraday's law becomes the curl of E equals negative partial B with respect to t. And then the curl of B equals mu naught J plus 1 over c squared partial b with respect to t. Okay, so I want you to see these equations and know that they exist. Mathematically, these are two different ways of writing the same equations. The way I actually get to these equations is by using what's called the divergence theorem and Stokes' theorem, which you might be familiar with from vector calculus. Although for practical purposes, we won't actually use these equations in any calculations in this class. Yes?
What is the P again for that first?
So this is rho, charge density. What this equation says is if you want a diverging electric field, you need a source. You need a source of charge, and that's what we've seen is positive charges are a source of diverging electric field lines. The second equation says that magnetic field doesn't diverge because there's no magnetic charge. That's what this equation says. This equation says that when you have a changing magnetic field, you induce an electric field which curls around that magnetic field. The final equation says you have a curly magnetic field whenever you have a charge current density or a changing electric field. Okay, so this says the same thing, but just in a different, well, using the language of vector calculus, yes.
Is that 1 over c squared?
1 over c squared.
And c being the speed of light?
C being the speed of light, yes. Yes.
What's the difference between flux with E, or like sub B or sub E?
So magnetic flux versus electric flux. So either it's electric field lines penetrating through an area or magnetic field lines penetrating through an area. Yes.
So what do we need to know this for?
Well, these are what we already know. This is a summary of what we already know. This, and this.
But the other ones?
Well, the only one we don't really know is...
No, all the stuff on the right.
Right, well, this is, all I'm saying is this is just an equivalent mathematical way to write it. Okay? All right. Now,
Yes.
so it looks like a lot of, in a sense, mathematical jargon, but it turns out that all of electricity and magnetism are just these 4 equations. This tells us how the fields behave, and really, if you were to think of it, these equations were discovered kind of gradually, but when they were all put together, these 4 equations describe everything that we know about electric fields and magnetic fields. So now you know a little bit of math. If you know a little bit more mathematics, you work with those equations, we know everything there is to know about electric and magnetic fields. There's one other thing which we could add here, and that is one other piece of information which we could add here which would complete the theory, and that would be basically saying that we know that charge is conserved. We've never been able to create or destroy charge, but you can only move charge from one area to another area. So charge conservation basically can be written as the divergence of J plus partial rho with respect to T equals 0. This is just a statement of charge conservation. And again, just I wanted you to see it, but we don't have to actually use it for anything. We've used charge conservation just to say, in this class, just to say when current splits at junctions, we know some goes some way, some goes the other way. And then finally, we only have one other equation, and that is the Lorentz force law. That tells us what the fields do to charges. Yep. And that's F equals Q multiplied by E plus V cross B. This is the Lorentz force law. Force law. Right, there's 2 ways to exert. If you have a charge Q, that charge Q is going to exert a force both by the electric field and the magnetic field. So there, I've just combined those 2 equations into one. Yes?
Is this E plus V cross B in the parentheses getting multiplied by Q?
Yes. Yes.
V in this case is velocity or voltage?
V is velocity. Yeah, the V cross B from the magnetic force, it's velocity. Right, so it's kind of a strange thing, because if I have a let's do a thought experiment here. It's kind of an interesting thing, because if I have a let's say I have a large solenoid. Right now, a solenoid produces a magnetic field. We produces a magnetic field that kind of looks like this. If it's a long solenoid, there's no current. There's no field here though. All the field is contained inside the loops of the solenoid. Now, those equations really tell us something very interesting, because if I take a loop of wire, let's take a conductor. This is just a conductor. And let's say I start to change the current that is going through the solenoid right here. A changing current through the solenoid produces a changing magnetic field. That changing magnetic field means that there's a changing flux through this big loop. So if there's a changing flux through this big loop, that means that there should be an induced current. So where does that induced current actually come from? Well, it comes from an actual electric field. So how do these charges know to move? There's no magnetic field out there. How do they know to move? Well, they know to move because this changing field in here induces an electric field which curls around that magnetic field and actually causes a current in this loop. Okay, so this is the basis of electromagnetic waves. Light is just an electromagnetic wave. When you have a changing electric field, you induce a magnetic field. When you have a changing magnetic field, you induce an electric field. And that's why light can travel from the sun or from distant stars to planet Earth through the vacuum. It doesn't need a medium through which to propagate because it's self-sustaining. Electric field creates, changing electric field produces a magnetic field, changing magnetic field in turn produces an electric field, and these processes are feeding off of each other, and the wave continues to propagate at the speed of light. It's all described by these set of equations, which are called Maxwell's equations. All right, so let's look at just some demonstrations here of this in practice. Now, here I have a magnet with two poles, a north pole and a south pole. Here I have a loop of wire and an LED connected to this loop of wire. So if I set this LED into the magnet, well, there's no power source, so we don't expect there to be any current, right? But if I rapidly change it, I can get the LED to blink. And notice, this is a one-way LED, meaning that it only lights up when I push it into the field. It doesn't light up when I pull in, but it flashes red. Actually, it flashes red because there's a changing flux through this coil, causes the mechanical motion of this loop actually causes the LED to itself light. All right, now I want to look at a few other examples here, some applications is so here I have an adjustable variable gap magnet. So this is the north pole, this is a north pole and a south pole. And in between this gap magnet I'm going to place basically two paddles. They're not touching the magnet at all. And let me just, it's easier if I just look at one of them here. So if I take this magnet, if I take this and swing it between the poles of the magnet, well, it kind of looks like a pendulum, right? It swings back and forth. But let me try the same thing with this paddle. Okay, so there is an example of, in a sense, magnetic braking, right? There's this backwards force as the flux through this paddle is a conductor. As the flux starts to rapidly increase as it enters the field between the gaps of the magnet, it produces that opposing force that we were looking at earlier on the screen, which basically halts the magnet or halts the conductor from moving between the poles of the magnet, so it stops immediately. Because of that swirling current, these are called eddy currents, and those eddy currents keep it from going. Now the fork one, it's hard for eddy currents to form in the fork because there's all these slots in the fork. So it can just, the eddy currents are so small that the fork can kind of just oscillate back and forth in the field and not experience that those eddy currents, which basically act as magnetic braking or magnetic resistance. So this is actually a dissipative force, because as you swirl a bunch of electrons around in a real conductor, that causes the metal to heat up. So the energy that was present in the paddle from its kinetic energy really does go into the sloshing around of the electrons and will warm the metal up itself. All right, so let's look at something similar here where I have everything's getting stuck here. Too strong. Okay, so here I have a copper pipe, and I have a strong neodymium magnet. Now, if I was to just drop something through this copper pipe, what's its acceleration? Gravitational acceleration. So I'm going to drop a magnet through the pipe. So the magnet falls a lot slower through the copper pipe, and regardless of which orientation I drop it through, pops out the bottom. Now, why might that be the case? Well, again, the explanation has to do with eddy currents. As you have an increasing flux right underneath a section of the copper pipe, right, the field wants to oppose it. That creates basically a little magnet underneath the magnet that's falling that always repels it. Those are eddy currents. Okay, now what happens if I get extreme here? Now this pipe is really heavy. Right? See how thick this copper is? I don't know how much this weighs, but now. All right, now let me try to drop this through here. We can just listen for the clink. It takes a long time. To be very patient.
Just gotta have faith.
All right, let's see.
You want to see what the camera down?
All right. So,
Yeah, I got that.
much more of an eddy current on this pipe just because it's so thick. Okay? Now, here's something very interesting. And I'm going to ask you to think about this one. I don't want to wait that long again. So I have a smaller chunk of copper pipe, but I have put a slot on it. I've slit it here. Now, how long is this one going to take to fall through?
Normal time.
Normal time? All right. So we still have eddy currents forming even with the slot on this copper pipe. Now let me take a sheet of copper and copper is not itself magnetic, but you can induce a magnetic moment when you bring a magnet towards it, so there's a bit of a force here. Now, something very interesting happens if I take this magnet and I try to pull it around. There's actually a force which is produced. I'll take a bit of a stronger. So there's a resistance, and I'll leave this up at the front after class, just on the corner here if you want to try it, because it's really weird. As you try to pull the magnet around, there's a resistance there. And this can be explained by Faraday's law. All right, so let's look at another example. You can also try the magnet if you want to after class. Just be careful, it's a little bit strong. All right, now, so here I'm going to turn on some current. Okay, so here's a solenoid. This is just a loop of wire, and when I press this button down, it basically turns the current on. So there's a rapidly changing magnetic field through this solenoid, just kind of like the one I've joined here, except it's vertical. So if I put a ring on here, nothing happens. But if I turn on the magnetic field, it hops up. Okay, now let me try it again. Interesting, this one doesn't work. Well, this one doesn't. This one has a slot on the side, so it doesn't actually want to jump up. Now what happens if I take an iron core and put it into the solenoid? Iron core, really, it beefs up the magnetic field because the iron becomes magnetic itself. So now, if I turn it on, and I get it leaping up this time, not just jumping up slowly. Thank you. So this is electromagnetic induction. There's a force that jumps its way up there. Now, what's a very practical use of Faraday's law? Well, I did mention last day about what's called power generation. Okay, so I have a little toy motor. And this toy motor works as follows. Here I have a loop of wire in between the poles of a gap magnet. And that loop of wire is sort of free to spin around. I can crank it this way. Now if I crank that loop of wire around in a magnetic field, there's a split ring commutator over here, which if I connected this to a galvanometer, if I connect it to a galvanometer and turn it, I get current. And the amount of current that I draw, so this would be an electric generator. I'm taking mechanical energy, turning a loop of wire in a magnetic field to produce current. And notice the current is always, this is DC current because the ring is a split ring, meaning the current reverses direction. Since the force flips direction every half turn, there has to be a commutator which keeps the current going in the same direction. Final thing which I'll show you here is, that's a generator, right? But let's say I want to turn this into a motor. Well, an electric motor basically takes electric power and produces mechanical energy. So I'm going to take this motor, connect it to a power supply, and have an electric motor which is converting electric energy to mechanical energy and actually giving me some motive power here. Just by turning a loop of wire in a magnetic field, changing a flux, right? And I can control the speed here just based on really how much current that I have. All right, so thank you very much, everyone, for a great class. I would appreciate if you could leave, you could fill out your student evaluation.